Alrighty, today what we're going to be talking about is Kirchoffs laws. Well, you guys have already learned some of Kirchoffs laws, but to remind you guys from our last PowerPoint about the total resistance of a circuit. If you have a series, which means they follow one after another, you add them up. It's just as simple as that. So you just take the resistor 1 plus the resistor 2 plus the resistor, all the way. You could have as many resistors as you want, and they're one after another. That will mean that they have to be added up. Now, if they're in parallel, meaning they branch, they have this node here, then you have to do the inverse addition. So 1 over R1 plus 1 over R2 and so on and so forth, which gives you the 1 over R total. So that is the parallel. Now, Kirchhoff's law comes from a gentleman in 1845. His name was Gustav Kirchhoff. He created two laws, one called Kirchhoff's current law and the one called Kirchhoff's voltage law. Now, Ohm, he took what Ohm did and added on to it. And then later on, a gentleman by the name of Maxwell, who's basically the father of electricity, took the work of Ohm and Kirchhoff and others and combined it to make the laws that we know them today. So let's talk about Kirchhoff's law. Now, these are the two laws. Please pause the video and write these down. Kirchhoff's voltage law says the sum of the voltages in this series circuit will equal the total applied. Kirchhoff's current law says the total current in a parallel circuit equals the sum of the individual branches. Write that down. We'll talk about what that means here in just a moment. So pause the video, write them down. Okay, so let's talk about Kirchhoff's voltage law. It says the sum of the voltages in a series circuit, that's important, equal the total applied. What that means is if you add up the voltages at every single resistor, it will equal the total voltage. So the total voltage is how much the battery is supplying. So here's our battery, and it's supplying 12 volts. That means that this voltage plus this voltage plus this voltage has to equal 12 volts. So 2 plus 4 plus 6 has to equal 12. That is Kirchhoff's voltage law. In parallel circuits, though, the voltage is the same throughout. This is 6, that means that this is 6, which means that's 6, which means that's 6. It's all the same. It does not change with a parallel circuit. Only with a series does it add up. Now, Kirchhoff's current law is literally the same, but flipping the word parallel and series. You literally just flip the two. So the current and the branches add up, and the voltages will stay the same. So the current will be the same. So again, if we look at the same circuit, we have a current of 0.2. That means that this is 0.2, this is 0.2, this is 0.2. Again, remember, it's like a river. Current's like a river. So the river doesn't split or meander. It will just go through. So whatever the current is going through here is going to be the same going through here, going through here. So no matter where you're at in the circuit, you're always going to have that 0.2 amps in this case, in this circuit. Now, Kirchhoff's current law in parallel circuits says the branches of the currents will have to add up to the total. So we have our total here. Well, it has to equal the 6 plus the 2 plus the 3. So my current total is 6 plus 2 plus 3, or 11 milliamps. So you can think of it. If I know point B's current and point C's current and point D's current, then I can add them all up to get me point A's total current. So let's look at an example problem. I want you guys in your notes, write down, draw this circuit, and what our goal is we're going to look at what is the current coming out of the battery, what's the current and voltages at every single resistor. So you can think of these as light bulbs. So every single light bulb, what is the voltage at that light bulb and what's the current at that light bulb? So the first step we have to do is find the equivalent resistance. Since this is a series circuit, we just add them all up. So we're going to take 3 kilo ohms plus 5 kilo ohms plus 10 kilo ohms. That's going to be 18 kilo ohms. Now, step 2 is to find the currents going through this. So how much is coming out? Well, we know the total resistance is 18 kilo ohms. We know the total voltage is 12 volts coming out of the battery. And so we can use Ohm's law, V equals IR, to actually solve for that. So we put it into the equation, V equals IR, and we put in 12 divided by 1800. Now notice it's 1800, not 18 kilo ohms. We had to change it back to ohms if we put it into an equation. So that puts it out as 0.00067, or we can put it into milliamps, which is 0.67 milliamps. Now, then step 3 is to find the current at each resistor using Ohm's law. So now we know that the current is 0.6 milliamps going through every single one. We know the resistance, 3 kilo ohms, 5 kilo ohms, 10 kilo ohms. So all we have to do is put them in. Again, remember, always can't use the kilos or the millis. You have to go back to their base units. So the 0.00067 amps times 3000 ohms equals 2 volts. The same current is again going through our 5000, and that's going to be 0.0067 times 5000, 3.33. And again, the 6.7 milliamps times the 10,000 ohms gives us 6.67 volts. So we're just using the Ohm's law, V equals IR. We knew I because that's our total. And then our R's are our individual resistors that are given to us in the picture. Now we can then confirm Kirchoff's voltage law. The voltage law said that in a series circuit, this plus that voltage has to equal to 12. So we can look. 2 plus 3.3 plus 6.67 is equal to 12. Now let's move on to an example parallel circuit problem. So here's another one. Now I want you to write this down. And again, you're going to work with us in your notes so you can follow along. So it's a slightly different circuit and it is different shapes. So this is a parallel circuit. So when we find the first step, which is exactly the same step, find the total equivalent resistance. So what we're going to do is we're going to take 1 over the R total is equal to 1 over R1 plus R over 2 plus 1 over R3 and so on and so forth. So we're going to do that. We're going to take 1 over 20 plus 1 over 40 plus 1 over 50 plus 1 over 25. And I put that in my calculator. That gives me 27 over 200, or in decimal format, it's 0.135. Now that's 1 over the resistance total. So I need to flip this fraction. So if I flip this fraction, I have to flip this. When I do to one side, I have to do the other. So I'm going to flip this, put the R total up top because I want that in the numerator. And then I'm just going to do 1 over that number. So that again is also going to flip my fraction. So instead of I have 227ths or 7.41 ohms total. So that's my total resistance. That's if I took all of these guys and replaced it with a 7.41 ohm resistor, it would work exactly the same. Now, step 2, we're going to find the total current, just like in step 2 of our previous problem in the series circuit. So then we're going to do is we're going to use exactly the same principle. We're going to use Ohm's law, V equals IR. We know our V, we don't know our I, but we know our total resistance is 7.41. So we put that in our calculator, and I say 100 volts divided by 7.41 gives me 13.5 amps. So that means that the electricity coming out of here is 13.5 amps coming through here. But as soon as it hits this branch right there, it's going to stop, and you cannot go down to the 20 or the 40 because it's going to split. So then what we're going to do is we're going to find the current at each resistor. Again, we're going to do the same thing, but this time it's a lot easier because the voltage is always the same. The voltage at resistor at the 20 ohm resistor is 100. The 40 is also 100 volts, 50 at 100 volts, 25 is at 100 volts. So all we do is we take 100 is equal to I don't know what it is, the current at the 20 amp times the resistance of 20. That gives me a current of 5. And when I do that down all the way, 100 equals I times 40, which gives me a current of 2.5. 100 equals I times 50, with the I turning into 2. And 100 equals I times 25, which gives me a current of 4. Now, I plug those. Now, what we can do is we can confirm Kirchoff's current law, which says, and that's supposed to be a C, not a V. Oops, my bad. The current then is going to be the sum of all of those currents. So 5 plus 2.5 plus 2 plus 4. I put that in and that comes out a current of 13.5, which if you look over here, our total current is 13.5. So it's exactly what it's supposed to be. Now, future classes, which you can take later on in your, not in this class, but in future classes, you guys can learn about more complex circuits where they combine series and parallels into a circuit, and you can get much more complex. But here's the really cool part. They are still have to obey by Ohm's and Kirchoffs laws, no matter how complex they look. These look scary, but they're not really that scary. They just look it. So if you have any other questions, please go ahead and ask your teacher.